Let's review for the second semester final. So, Unit 7 was on momentum. Here are the main important ideas you need to study. First of all, you need to know what the definition of momentum is. Okay. So where momentum is equal to mass times velocity. And we abbreviate P equals m times v. Next thing you need to understand is the impulse momentum theorem. Okay, now the impulse momentum theorem says this: if I apply a force for a period of time, that's called an impulse. That impulse will result in the change in momentum of an object. So if I apply a force for a period of time, that equals a change in momentum. Change in momentum, not the final momentum. And because this is a product, force times time, I can draw a graph of force as a function of time. And maybe the force doesn't stay constant with time. Maybe it changes, ramps up, and reaches up some maximum value, and then comes back down. The area underneath this graph is the product of force times time. That area is your impulse. That area is equal to the change in momentum on your object. So on the final, I could give you a little graph like this, and if you figure out the area underneath that graph, you've got the impulse. And if you've got the impulse, you can figure out what the change in momentum is. And usually, by the way, if you have a change in momentum of an object, that's if the mass of the object will stay constant. I'm not going to give you a problem where the mass changes with time. So that's going to be mass times a change in velocity. So I might ask you how much the velocity changes. I could give you a graph like this and say, if this object has this force on it, what's the impulse? What's the change in momentum? What's the final? If the initial velocity is 10 meters per second, what's the final velocity going to be? You know, something like that. So there you go. The other main idea with momentum I want you to note for the final is conservation of momentum. And you need to know, if the net force is equal to 0, if there's no net force acting on your particle or on your system of particles or on your object, there's no net force on your object, then P initial equals P final. The initial momentum of your system will be equal to the final momentum of your system. Momentum won't change. And an example of that is our collisions. When objects collide, yeah, they apply forces to each other, but those forces are equal and opposite to each other. And so the initial momentum you had before will be equal to the final momentum after. And I would go back in your notebook and find a couple of collision problems and make sure you know how to solve a collision problem, because there will be a collision problem on the final. It also works for explosions. Explosions are essentially the same thing as collisions, except that usually the objects aren't moving and two objects push each other apart. Okay, they apply equal and opposite forces for exactly the same period of time. That means equal and opposite impulses, which means equal and opposite changes in momentum. So when you add those changes in momentum together, you get no net change for your overall system. So study your collisions. And that'll be enough for Unit 7. You know all that, know how to handle that, you're good. Okay, Unit 8 was work and energy. Oops, let's go up here. And work and energy. Well, first of all, make sure you understand what energy is. Energy is the capacity to make a change in your environment. If you've got energy, you can change something. If something has zero energy, it can't do anything. So energy is quite literally the ability to do something. Okay, and it comes in many, many forms. I'd like you to know what those forms are, or the way energy exists in nature. You have the energy of motion, which we call kinetic energy. Objects that are moving can make a change in their environment. If you don't believe me, go play on the freeway, okay, and you'll find that those moving cars can make a change to your environment, perhaps a permanent one, okay. Objects that are moving, if they have mass, they can make a change. Now, the equation we have for kinetic energy is K equals 1/2 the mass of the object times the velocity squared. Okay, now we proved that. We showed why this is true. So you might want to review that. Then we talk about the energy that gravity, the work that gravity can do. If I hold a bowling ball, 20 feet over your head, that's got a lot of potential to make changes to your environment once again. If you ever drop something on your foot, that something has mass and it has height in a gravity field, it can make change. So we call that gravitational potential energy. Okay, and we abbreviate that with the letter U sub G. Time it's a potential energy, we use U. And then the subscript means G is for gravity. And that's going to be equal to mg is the weight of the object times the height, h, above some reference point. So this is your height of the object. This is the mass of the object. That's the acceleration of gravity, or the gravitational field strength, 9.8 newtons per kilogram here at the Earth's surface. We have elastic potential energy. And elastic potential energy has an equation. I think we only used it once, but it's 1/2 K x squared. Now what is this K? It's not the electric constant that we just did. It's the spring constant. It's a measure of the stiffness of the spring. It's measured in newtons per meter. It's how many newtons of force you need to stretch or compress the spring 1 meter. And then this is how much you stretch or compress the spring, the x. So it's just to measure how much energy it takes to stretch, or how much energy is stored. If you stretch a spring, obviously that stretched spring wants to pull back, and so it's got energy stored in it. Now there are other kinds of energies that we didn't have a formula for, but such as chemical potential energy, that's the energy stored in food, in fat, in gasoline, kerosene, whatever. Anything that will burn has chemical potential energy in it. Okay. Some of you are eating cheese right now. There's chemical. Oh, apple. That's better. If you're eating an apple, there's energy in the way the molecules are arranged, and your body has a way of taking advantage of that. That's called chemical potential energy. Now, then we have work. And work is the way we transfer energy from one system into another system using force. So this is a transfer of energy using force. So if you throw a baseball, for example, you're transferring energy out of your arm and into the motion of the ball. The ball now has kinetic energy. It didn't have that energy before you threw it. And that's because you applied a net force to the ball, giving it kinetic energy, but that cost you energy. I mean, you had to use some of the chemical potential energy in your arm and twitch your muscle fibers and all that. So, and that's why pitchers get tired. If you throw a ball all day long, your arm's going to wear out. You're going to need some recovery time. For any kind of sport. Oh, that's true. So it's a transfer of energy. Now, there is a formula for work. Work is equal to the force that's applied times the displacement, and I call it a distance if you want, but it's how much, what displacement you move through. We can call it delta x. And then but it doesn't have to be in the x direction. It can be in the y direction, any direction you want. Times the cosine of the angle between the force vector and the displacement vector. Now, those of you who are in AM or AMA, you did this. This is called a dot product, or a scalar product of two vectors. It's F dot, I'll use delta R. That's a more generic displacement. This can be in any direction, not just the x direction. What I'm going to do on the test, if you know this on the test, that's good enough. But notice that if your force is opposite in direction to your displacement, you can do negative work. If negative work is done, that means you're transferring energy out of the object. Like if something is moving at you and you push on it to slow it down, you're taking away its kinetic energy. You're doing negative work on it. Yes, real quick.
Is delta x cosine beta, they're together, right? Or
they're multiplied. Yeah. Okay. All right. Then we have the concept of conservation of mechanical energy. If the only force doing work are gravity or springs, then all you're doing, if gravity does work on an object, it's going to slow the object down or speed it up, but in any case, that energy is turned into kinetic energy. Or it turns kinetic energy into gravitational potential energy. If a spring is doing work, and it's the only force doing work, it's taking kinetic energy and it's converting it into elastic potential, or converting elastic potential into kinetic energy. Okay. And so that means that, so if and only if, IFF, you've seen that before? IFF, if and only if. The only forces doing work are gravity and springs, or any kind of elastic material, then E initial equals E final. Now, what does E stand for in this case? Mechanical energy. And E, mechanical energy, is defined to be the sum of kinetic energy plus potential energy. This could be gravitational or elastic. So, an example of that would be a roller coaster problem. Now, I did a whole lecture on Mr. Lake's Wild Ride and how to solve roller coaster problems. I'm just telling you, in honor of the seniors going to Magic Mountain for grad night, there will be a roller coaster problem on the final. It'll be a simple one. Then you'll have to do it in the honor of those who are going to grad night. So, what if? Rosa, enough with the what ifs. All right. One thing I should have put it earlier. It doesn't really matter, though. And that is the work energy theorem. And what the work energy theorem says is that if you have a whole bunch of forces acting on an object that are doing work, if we add them all up, you get the net force. And the work done by the net force can only do one thing. It will change the kinetic energy of the object. The work done by the net force will be equal to the change in the object's kinetic energy. So look for this. F net, and the way to read that is the work done by the net force will be equal to the change in kinetic energy of the object. So I can give you a problem where I give you the, I'll give you a net force, and you figure out how much work was done by that net force, and what happened, what did that work do? It changed the kinetic energy of the object. It didn't change the gravitational potential energy or the elastic potential or the chemical potential. No, it changed the kinetic energy. That's the work energy theorem. Okay, so study all that. Now we'll do Unit 9. This was on thermodynamics. Okay. Thermodynamics. Here we're dealing with heat. First thing you need to know is what is temperature and how to go from Kelvin to degrees Celsius. I'm not going to put anything on degrees Fahrenheit on the test. Then we're going to talk about heat transfer, which we call Q. Now, heat is when I'm transferring thermal energy. So make sure you look. Thermal energy is the energy due to the vibrations of atoms and molecules. So if things are very cold, they're not vibrating very fast. They have a low temperature. They're probably in a solid state. But if you increase those vibrations, you can raise the temperature of the material. You're increasing the thermal energy, so you can increase the temperature. Or if you increase the vibrations so much, you can tear apart a solid and turn it into a liquid. Or the molecules fly apart altogether and you vaporize it. It goes from a liquid to a gas. So that's all by transferring heat. Heat is the transfer of thermal energy measured in joules. We're going to use joules in here, not calories. And remember that if I add heat to a substance, I might change its temperature. Depends on the amount of heat, depends on the mass, the specific heat capacity, and how much I change the temperature of the object. So I can put heat into an object, a certain amount of stuff with a certain specific heat capacity, I'll increase the temperature. But what if I extract heat? If I extract heat, Q will be negative and the temperature will drop. Okay? Or I can melt an object and how much stuff I have, and that's the heat of fusion. So review that. Heat of fusion, that tells us how much energy it takes to melt a certain quantity of a solid material. So I take a solid material, I add heat to it. It doesn't increase in temperature anymore, but the solid falls apart. It takes work to do that. It takes energy to do that. And so it will melt into a liquid. Now conversely, what if I want to take a liquid and turn it into a solid? I have to extract heat from it. If this is negative, that means I am extracting heat. And this tells me how much energy I have to take away from the material to make it freeze. Now you put ice cubes in your freezer, you have to lower the temperature. And once the temperature is at 0 degrees Celsius, you have to extract more heat in order to allow those water molecules to slow down enough so that they can actually connect to each other into crystals and stuff and make a solid. If I want to vaporize a material, that is, I want to boil it away, turn it from a liquid to a vapor, you have to use the heat of vaporization. Now, don't worry about heat capacity, specific heat capacity, heat of fusion, heat of vaporization. I'll give you a little table that has all of those things on it. And so make sure you understand what these things are. Now, finally, entropy. There's no equation for entropy. Entropy is the tendency for systems to go from a level of high organization to low organization, from a highly ordered to more disorder. So the level of disorder in a system is called entropy. Systems will almost all, in other words, if left to themselves, they will always fall apart. Okay. Review heat engines. Heat always flows from a high to low temperature. High temp. Heat will flow from high temp to low temp. This is another way of saying that entropy always increases. You'll never see stuff all by themselves where you put an ice cube in water and the ice cube will get colder. I'm sorry, the ice cube will grow. Okay, or if I have a hot cup of coffee, the coffee will not get hotter as the room gets cooler. It never goes in that direction. The heat will always flow from high to low temperature, always. Now what we can do as this heat flows, I can build a device like a steam engine or in a car an internal combustion engine to turn some of that into useful work. So this is the heat that flows out of your high temperature source. We get a little bit of work. We also have to dump some into our low temperature source. And this is expressed, energy has to be conserved because the heat that leaves my high temperature source will be equal to the work done plus the heat that's dumped into my low temperatures. And the heat that's dumped into low temperature, it's kind of like the exhaust pipe on a car. Okay, so this is conservation of energy, and the direction of the heat flow is the second law of thermodynamics that says that overall entropy in a closed system will always increase. Overall, heat will flow from a high to low temperature. Okay, so that's Unit 9. The highlights from Unit 10. And I got to speed up. I only got a few minutes left. Unit 10 was all about electricity. And I want you to know what charge is. We've got two kinds. Positive. What carries the positive charge? Protons. What carries the negative charge? Electrons. Of course, they didn't know that at the time. Charge is measured in coulombs. A coulomb of charge is a huge amount of charge, huge number of protons and electrons. Okay. 1 proton has 1.6 times 10 to the negative 19 coulombs. You can reciprocate this to figure out how many protons there are in a coulomb of charge. The electrons have the same amount of charge, it's just that we call it negative instead of positively charged. I want you to know how to use Coulomb's law. Okay, so, which says that the force of attraction or repulsion between electric charges, if they're concentrated at points in space, is the electric constant times Q1 times Q2 over R squared. Looks just like the law of gravity in the R hat direction. Know how to use this. And what is K? Yeah, 8.99 times 10 to the 9 Newton meter squared per coulomb squared. These units here cancel out with these guys to leave newtons, because that's what force is measured in. And this is a property of our universe. Turns out electric force is pretty strong. And I want you to understand electric fields. Electric fields are a way of visualizing or imagining what's happening in the space around a charged particle. If I have a whole bunch of charge somewhere, if I put a test charge right here, I'll call that Q naught, this is Q, they will repel each other, and I measure that force of repulsion, and I divide it by the test charge. And that, by definition, is the electric field at that point in space. And we can connect all of these force vectors together to make what's called an electric field line around the charge. And please review the rules for electric field lines. And I'm going to leave you to do that because we are running low on time here. Now, from electric fields, we define electric potential, which is another way of saying voltage. And the electric potential, V, is equal to the electric field dotted with the displacement. I'll just call it E. We'll just call it E times D. I'll use the D. That's what the book uses. I don't like using D for displacement, but there you go. So if I do work against an electric field, I'm gaining electric potential. And notice what this has. Electric field is measured in newtons per coulomb times a displacement measured in meters. Newton times a meter is a joule. Joule per coulomb is called a volt. That's the unit for electric potential. So you might have to use this. Now, the electric potential energy, which I'll call U sub E, is just charge times electric potential. This is joules per coulomb times coulombs. You'll get how much energy is stored there. And finally, under electricity, what we just did, there'll be a problem on DC circuits. So you have a voltage source, a series of electric cells, we call that a battery. It has a certain voltage, it puts out a certain current. You run it through something, we call that a resistor. And I'm having to rush here because we only got 2 minutes left, but this is most familiar to you, so I'm hoping that you'll be able to get this. We have two equations here. The power that this puts into a circuit is equal to current times voltage. Close that door. And then resistance is defined to be the amount of voltage I need to get 1 amp of current to flow through something. And a volt, this is a volt per amp. the unit of resistance, a volt per amp, is called an ohm. So make sure you understand how to use these two equations to solve very, very simple DC circuit problems. And they'll be that easy. Okay, I think that's enough to keep you out of trouble over the weekend. Good luck, and see you on Monday.